Welcome to this talk on AI on maintenance data, challenges to value delivery. My name is Melinda Hodkowitz and I work at the University of Western Australia. And I've been in maintenance for probably about 30 years and have seen some major changes and maybe some not so major changes in that time. So like a lot of people, I've been watching with a certain amount of initially excitement and then horror of the hype surrounding the promise of predictive maintenance. Predictive maintenance as an idea and linked to condition monitoring has been around for 25 years. This is nothing new, but it's received a lot more attention recently due to various technical and other changes. And as you'll see on the slide, these are some data from various reports from people like GE Digital and McKinsey's talking about predictive maintenance being the killer app of industrial IoT, predictive maintenance generating the highest business value for organizations with heavy assets, and new technologies yielding up to 30% in maintenance cost reductions. So obviously, there is a huge prize out there, potentially. But let's look at this in a little bit more detail. The reality. A study by McKinsey's in 2020 suggests that 70% of all maintenance transformation efforts fail. And that certainly as far as AI goes, companies are trapped in endless small-scale piloting and experimentation that never really delivers value. There is a growing realization that corporate systems are not ready for the complex solutions that AI involved, that need to be capable of predicting solutions before they happen. They're okay if all you want to do is run AI algorithms on data sets you've had in the past, on test and training sets, but the whole process of running those same algorithms on unseen data to predict something that really might happen and to do that reliably and take action on it before the event occurs is entirely a different matter. As a result, we have a legacy of doomed asset health initiatives, battle scars on people who've tried them, careers lost or damaged by promises not fulfilled from the adoption of asset health and predictive maintenance improvements. This is not specific to any one sector. There is evidence that there has been problems with this across many sectors. And as a result, we've seen in 2016 it was all go. In 2018 it was let's be a little bit cautious. And in 2020 I think it's fair to say it's let's be very cautious about which projects we choose to follow up on and why. So when we think about AI on maintenance data, let's think about what could possibly go wrong. So first of all, we need to think about maintenance data in general. Maintenance is a big area, and there are many places that we can focus AI on. And I'm going to talk a little bit more about that. But 4 things that we should really be asking ourselves, not just with the application of AI to maintenance, but the application of AI in general. First of all, do we have the right data for whatever it is we want to do? Are the data biased in some way? What about the algorithms? How do they work? Are they robust? How do we assure ourselves that they are robust? Do we really understand what we're predicting? And I'm going to come back to this in a little while because it's my observation that actually often we don't. And even if we could predict this, when the people that do the algorithms move on to something else, how do we manage this very considerable skills uplift in all aspects of data management in order and to actually get the data pipeline that delivers the recommendation that we need through the business? And then again, how to manage the human in the loop in all of this. Where do humans need to be in the loop, and how do we make sure that they are sensibly and supported and needed, that their intelligence and experience is incorporated into this. So we don't, I think, ask ourselves nearly enough as we sort of throw data scientists at various problems and data sets. Here's a data set, go tell me something about it sort of approach. We don't often ask, what actually is AI good at? It's not good at everything. And I'm going to talk about what I think are three really areas we should be focusing on. So the first is truly repetitive processes with a narrow scope for which data is available. And what does that mean for us in the maintenance world? It means fault detection on fleets, where you've got very similar, if not identical assets. You have lots of them, therefore you have a large number of similar events occurring in similar conditions. AI could be really good and is proving to be very useful in these sorts of situations. Technical language processing and generation, I'm going to talk a little bit more about that, and in terms of automating some of the reporting that, again, reporting is a repetitive process with a very narrow scope. AI is also very good for hypothesis-based pattern identification, so anomaly detection and classification. It can be very useful. Neither of these are predictive tools, but they do help us understand data and to be able to analyze and identify things that might be of interest to us. And then in narrowly defined situations with clear rules, such as in games and training. But that's actually not where we often see AI applied. We often see AI applied to really one-off problems where we've had a massive failure. And the idea is, boy, we want to be able to make sure this massive failure doesn't happen again, even though it's only happened once. We may have been operating this piece of kit 24 hours a day, 7 days a week, 365 days a year for the last 10 years, and everything's been fine. In which case you've got an awful lot of data for what good looks like and very little data on what bad looks like. And yet stochastic models need, particularly deep learning models, need very large volume of input and output data. And by output data, it means you want to have lots of examples of where the problem has occurred. And if you don't have that, because we have very few failures, then it can be very, very difficult to train your models when you have unbalanced data sets. There are methods, but they need special attention and often quite specific statistical expertise. We also, I think, underestimate the number of factors that affect individual asset life trajectories. So we assume that when we have a problem that it's the same failure mode progressing often, and then we don't necessarily, and find it very difficult in our models, to take account of during that life when maintenance was done or not. So whether we've reset the condition of the asset during its life. And we don't often see this information if we're just looking at asset health data, because the asset health data on the screen won't necessarily tell us what interventions have been done during the life of the asset. Obviously, it's sometimes obvious if the asset health has improved, we might go looking for, I wonder why the numbers got better. But in the absence of that, we have to look at other data sets, and that can be problematic because it's time consuming. And the other thing is the input data should cover the range of all possible events, because AI only learns what it's seen before. So for every event that you want to predict, every failure mode you want to predict, you actually have to have a really nice set of input data and known trajectory data in order to do those analysis. And this is one of the reasons why fleets are particularly good for deep learning and other models, but many other things are not. I mentioned at the beginning of, do we really understand our data? And I was involved in some really interesting work a couple of years ago on fleet management system, and we were asked if we could predict failures, failure or fault events from all the fleet management data. So we had gigabytes of data, something like 70 variables and binary indicators from which to predict data, and we had what we thought were a lot of events. But as we started to look in detail, we made our models, and they were overfitted, so they predicted really nicely on the training set, predicted horribly on the test set, and we started to unpack the data a little bit more. And I think this is emblematic of the need to really be close to the data and the people who know the system. So in our case, was the hydraulic faults. We had these codes, hydraulic codes, that were in the fleet management system, but it turns out those codes are put in by an operator. And it wasn't apparent to us for quite a while that those codes weren't real, that they weren't true. They were the operator's view about what the fault could be caused by at the time they were on the machine. So you've got 4 operators a shift. They all think about these things differently. We were really clued into this by the fact that almost none of the faults that were identified, which are shown in orange on the left, lined up with any sort of maintenance, subsequent maintenance repair. So if you've got a hydraulic fault and it never goes to the shop for maintenance, it probably wasn't a hydraulic fault. And once we realized this, lots of other things fell into place. So that's what I mean about being really careful to understand where your data is coming from and whether there's a human in the loop there, because with oil analysis and all vibration analysis, all of those things are interpreted by humans. So you're not actually mapping truly the health of the equipment. You're mapping the interpretation of a human about the health or state of that equipment. And you have to take that human interpretation into account. And it's often not very repeatable. One of the other issues that we have seen for quite some time around predictive maintenance is there are many steps to success. Let's assume for a minute that you're pretty sure that you've got a reasonably good system. So what this swim lane chart is showing you is on the left-hand side. You can see there are 5 different roles involved in 3 different maintenance strategies. So the 3 strategies are finite, fixed interval, condition-based maintenance, and predictive. And you've got various roles involved in this. Obviously, fixed interval maintenance is really requires very little input. It comes out of the computerized maintenance management system, it gets approved, and it gets executed. Very little overhead involved in that. Let's look at the other hand about condition-based maintenance. You get a work order to collect data, condition data out of the system. It needs to get approved. You need to send a Conmon technician out to do it. They need to come back. It needs to be identified. If the fault's identified, you have to create another work notification. The work notification needs to go into the CMMS system. It needs to be approved, and then you need to execute the work. And a similar thing for predictive maintenance. So obviously you've got models involved there. So at any one of those steps doesn't work or gets delayed, you're not going to actually be able to execute the work before the failure occurs. And I think this is an underestimated problem in terms of delivering value. You can do all the work up front to collect the data, but actually value is only delivered when you actually, certainly in the Conmon and the predictive, do something in a timely manner ahead of failure. In other words, do the execution in the red box. Otherwise, all you've done is create costs and no value. So one of the other places to look for easy wins, as I mentioned at the beginning, is that over 70% of data in organizations is unstructured text. Estimates from Deloitte are that the search for information takes 14 to 30% of the engineer's time. So just to do any sort of analysis or calculations, reliability engineers spend an inordinate amount of time looking through work orders, looking through root cause analysis, looking for oil analysis results, checking with vibration data. It's an extraordinary impost, and it's time consuming and not very interesting to do. And every time you repeat the exercise, you have to go and do it all over again. There's no sense of once you've done it once, you don't have to do it again because you've got a method. No, you have to get back into Excel and search and structure things all over again. So what we've been working on for the past 4 or 5 years is really using the power of AI to allow engineers to view asset text data, particularly that locked in maintenance work order records. So we have done work also on procedures and safety records. And it's too short a talk here to talk about why every reliability engineer needs to know what knowledge graphs are, but I've got some references coming up on the next page. So this is just a picture which basically shows a cartoon of a knowledge graph where you can see functional locations are shown in yellow, the asset type is shown in green, and you can see from those nodes have connections. For example, has observation, in other words, a link to a failure mode, and these come from the observations in the short text of work orders, and also has activity. And one of the really cool things about knowledge graphs is the ability to connect different data sets together in a relatively straightforward way. So in this particular example, we were able to connect the colored nodes that you see on the left-hand side, which all come from maintenance work order, from the short text of maintenance work orders, and from the functional location field. We were able to connect that straight to AMPLA or downtime data. So we know exactly what failure modes have and how many and what the impact in terms of downtime were. And obviously trying to do this routinely for maintenance engineers is very useful, but also using non-AI based methods, very tedious. So technical language processing, which is sort of an overarching encapsulation of natural language processing, knowledge graphs and ontologies, is really about the provision of an emerging range of tools for reliability engineers to use. And we've been working at the Centre for Transforming Maintenance Through Data Science and at the NLP-TLP group at UWA, and with a host of other research organisations around the world, to really look at three things. First of all, to efficiently identify end-of-life events, both failure and suspensions, from maintenance work orders, so that these can be used for Weibull analysis. To discover and quantify actual failure modes experienced by the equipment, and then being able to compare them with what was expected from FMEA. And this then leads on to you being able to check and see if you think your strategy is right. Are you getting the failure modes you expect or not? And also quantify what work was done and when. As I mentioned earlier, all this is largely done manually currently by engineers, but in our view, it can be semi-automated. And I've provided a set of links there. If you're interested in more information, please go and have a look at the web pages, GitHub sites, and recordings for more information. And finally, it's no good in the modern day organization, corporate, to be just doing something cool on your computer on your own. Really, if it's going to deliver value over the long term, you really need to be part of the corporate systems. And so if you start to think, well, I'm going to have my little ML model sitting on my computer over here and everything will be dandy, it won't, because it's very dependent on you. And if you get moved, or you get distracted, then that doesn't work. We really need to be thinking about storage and scaling and governance of the various algorithms. So my advice is, if you don't have that in place, you really probably need to be getting that in place early on in your journey towards using analytics of any sort and AI of any sort in your organizations. And you treat it just like any other governance process. You understand the business requirements, you understand the risk, you have processes to manage that, and you have controls in place to make sure that the processes are in fact being followed. So my final comments is really just a suggestion, maybe even a plea to people to focus on what AI is good at and understand its limitations. Not to ignore the opportunity of the automation of automation of slow, repetitive and tedious processes that reliability engineers currently do. If you can free up their time, that's an enormous productivity boost for them to go on and do more value-adding work. Concentrate on things that can be standardized and scaled through adoption by others in the organization, and have governance systems in place to manage the pipelines you develop. I hope you found this interesting. Thank you very much.